homework.
Look around your classroom. What do you see?
For which one?
There are probably desks and chairs, calculators, pens, and maybe a chalkboard or a whiteboard. All of it is matter. And matter is just another word for the materials that are all around us. In fact, everything around you is matter, even the air you breathe. Matter can exist in three main states: solid, liquid, and gas. A solid is a substance that has a definite shape and volume.
You gotta make one of the books blue.
Solid matter retains its shape, like the chair you're sitting on right now. A liquid is a substance that has definite volume but no definite shape. Liquid is a matter that can flow while keeping a constant volume, like milk or honey and lava. A gas is a substance without a definite volume or shape. You cannot see many gases, like the oxygen we breathe or the helium that fills up a balloon. Solids, liquids, and gases can change from one state to another. One of the best examples of matter changing states is also one of the most plentiful and important types of matter on Earth. It covers 70% of the planet, and without it, life itself would not exist. Can you guess what it is? Right, it's water. Like other kinds of matter, water can be a solid, a liquid, or a gas, depending on its temperature. When the temperature is 0 degrees Celsius or below, water will be in a solid state, like ice cubes, an ice rink, or a frozen lake. The particles that make up solid matter move much more slowly than the particles in liquids and gases. Between 0 and 100 degrees Celsius, water is in a liquid state. The particles that make up water move around more than they did in the solid state, gliding past each other. Above 100 degrees Celsius, water evaporates or turns into water vapor, which is water in a gas state. The particles in water vapor are far apart and move much faster when compared to the particles in liquid water or solid water. Water is continuously changing states on Earth. The movement of water as it changes states is called the water cycle. Water vapor makes up part of the air. As water vapor rises and cools in the air outside, it changes into tiny droplets of liquid water that form clouds. Many people think that clouds are made up of gas, but in reality, clouds are droplets of liquid water that aren't heavy enough to fall. The droplets combine and grow larger and eventually fall as rain, snow, or hail. Rain is liquid water, and snow and hail are solid water. That rain, snow, or hail falls to the earth and makes its way into the lakes, rivers, and oceans. Water on Earth from the rain or snow will eventually evaporate or change back into water vapor. The water vapor will change into droplets of water and form clouds in the sky, and the water cycle will start over. Hydrologists are scientists who study water, the water cycle, and the impact water has on human life, like Peter Richards at Heidelberg University.
I think the thing that's most important to me thinking about the water cycle is to try to figure out how we may be impacting different aspects of that cycle.
If the air temperature changes because of climate change, we could see changes in the water cycle itself. That's because warmer temperatures cause water vapor to evaporate faster. This means it could rain more often and even affect how much water is in lakes, rivers, and oceans. So we just learned a lot about water. It can be a solid, liquid, or a gas. And the water cycle is just one real-life example of how matter changes states. Remember that all matter can change states. Most matter changes states at temperatures much colder or hotter than we normally experience. For example, metal can melt from a solid to a liquid. It's how metalworkers shape things like horseshoes, tools, and even jewelry. Lead melts at a smoldering 327.5 degrees Celsius. And gold? Even hotter at a whopping 1,064 degrees Celsius. Now it's your turn to observe how water changes states. Leave a cup of water out on the kitchen counter. What do you think will happen to the water over time? Can you think of some more things that you can do that'll change the state of water?
Solid, liquid, and gas, the OG states of matter, the terrific three. And then came plasma, and then there were four. And then you may have heard that there aren't four, but 5 states of matter, including Bose-Einstein condensation. But what if I told you there aren't 5, but 22 states of matter? Let's play that intro. Okay, don't start yelling at your teachers for telling you that there are only 4 states of matter, because they are right in the sense that solid, liquid, gas, and plasma are the only naturally occurring states on Earth. But there are so many other states of matter that play a very important role in the composition of our universe. A really important one is quark-gluon plasma. It made up the universe a few milliseconds after the Big Bang and is the reason for many stars and planets today. Fun fact about this, it is the hottest thing known to man, with temperatures exceeding 10 trillion degrees. That's 100,000 times hotter than the center of the sun. And the element on Earth with the highest boiling point, tungsten, will vaporize instantaneously anywhere near this. Wow. Another space-related state of matter is degenerate matter, a highly compressed state of matter that's found in dead stars. Okay, let's get back to planet Earth and look at some states with really weird properties. Superfluids. The most common example is liquid helium. Something that we can make here on Earth by cooling helium to just a few degrees away from absolute zero. By doing this, we are turning it into a superfluid. Its new properties include being able to flow without any friction and having zero viscosity. So, in a nutshell, if you started stirring a superfluid in a cup, you can take the spoon out and the superfluid will never stop moving. You thought that was weird? Then you need to check out Rydberg polarons. A Rydberg polaron is an exotic state of matter which occurs at extremely cold temperatures in which an atom contains other atoms inside of it. To make this, scientists had to combine Bose-Einstein condensates with Rydberg atoms, which brings us to our next state of matter, Bose-Einstein condensates. A Bose-Einstein condensate is a state of matter considered the 5th state of matter that was predicted, as the name suggests, by Einstein and Satyendra Bose in 1925. This is a pretty complicated subject involving quantum mechanics and complex chemistry, so I'll try to simplify it as much as possible. It's basically a state of matter where separate atoms or subatomic particles are cooled to near 0 degrees Kelvin or about negative 460 Fahrenheit. This causes all of them to occupy the same quantum state. I'm not going to go in depth in this video about this, but if you're still interested, I'll have some links down in the description. Let's look at some super states of matter, alike superfluids. There is supersolids, which are solids that are able to move without any friction whatsoever, but still maintain its rigid and hard shape. The other one is superconductivity, a state of matter in which the object has exactly 0 electrical resistance. It's pretty much the ground state of many elemental metals. Alright guys, that about covers the most commonly occurring weird states of matter that nobody talks about, but there are still other ones. Other states of matter that are extremely rare and only occur under very specific conditions include supercritical fluids, excitation, fermionic condensates, self-induced spin glass, stringnet liquids, droppletons, Dijon Teller metal, and time crystals. Thank you guys so much for watching. If you enjoyed or learned something new in the video, I really suggest subscribing because there's a lot more of that coming your way.
You guys, this is crazy. Scientists have created a whole new kind of matter. Yeah, time crystals are here. Hey there, Time Bandits. It's Trace for D-News. Physicists have created a new form of matter called time crystals. No, not the time crystals that you may have seen on Rick and Morty. These time crystals have properties we have never before seen in other matter. Usually, matter is motionless at its resting state and only has potential energy until kinetic energy is introduced to it. For example, a ball at rest is chock full of potential energy, and when it's kicked, that energy is converted to kinetic energy, the energy of motion. But time crystals actually move at their resting state or ground state, and that's when atoms have the lowest amount of energy. They're like a ball that is forever in motion. In other words, they are always unstable, down to the atomic level. They are the first non-equilibrium matter ever created. Regular crystals are an arrangement of atoms in repeated three-dimensional patterns called a lattice. The patterns are duplicated through space, whereas time crystals duplicate their patterns through space and time. They are essentially four-dimensional crystals. The concept of time crystals was first theorized by Nobel Prize winner Frank Wilczek in 2012. He surmised that there could be hypothetical matter that could move periodically even while in its ground state. In theory, the time crystals could move without the application of energy because they would be designed to be inherently unstable, breaking the symmetry of time, resulting in atoms that are in perpetual motion. Once the theory of time crystals was out there in the ether, researchers focused on coming up with methods to create this new matter that could break time symmetry. A blueprint was created and posted online in August of 2016. The author called his paper, quote, "the bridge between the theoretical idea and the experimental implementation." Two teams, one from the University of Maryland and one from Harvard, took the basic blueprint of how to make time crystals and both got to work. Both teams were successful but used different methods to achieve the same time crystal results. The University of Maryland created their time crystals with a line of 10 ytterbium ions. Within these ions, the spins of their electrons were entangled. The researchers' goal was to interrupt the ions' normal equilibrium. To do this, they used two lasers, one to flip the ions and a second laser to create a magnetic field. The first laser flipped ions over, causing them to interact with other ions, making them flip over, all within the magnetic field created by the second laser. This process continued until all the ions were oscillating or spinning. This was considered normal behavior for a regular crystal, but researchers noticed something strange. As the lasers continued to nudge the ions, they realized that the ions were now reacting more frequently than they were being nudged. According to researcher Norman Yao, this is like jiggling jello and have it move when you weren't poking it. Researchers had essentially broke the time symmetry and created a new form of non-equilibrium matter that continued moving even at the ground state. Voila, a time crystal. Researchers at Harvard went about creating their time crystal differently. Instead of ytterbium ions, they used nitrogen vacancy centers, which are certain impurities found in diamonds. And instead of using lasers, Harvard researchers used microwaves to cause the ions in the diamonds to flip and oscillate. Different method, same result, time crystals. This new form of matter could lead to future breakthroughs in quantum computing and understanding the various forms matter can ultimately take. Researchers have also remarked that their creation of time crystals is evidence that time symmetry can be broken and that non-equilibrium matter can exist. If you want to know more about quantum computing, check out Crystal's video on quantum computers here. Let us know down in the comments what you think about time crystals if they blow your mind a little bit. Make sure you subscribe for more D-News, and thanks for watching.
I don't know about you, but if I was on a ship and I saw a glowing sphere of light suddenly floating around the top of the mast, I would be, I think this is the proper term for it, freaked out. But for centuries, sailors saw that all the time, and they thought the mysterious blue glow was a good omen because they associated it with the end of a storm. They called it St. Elmo's Fire, after St. Erasmus, the patron saint of sailors. But we now know that it's a natural phenomenon. When the pointed end of a ship's mast interacts with the heavily charged air, like during a storm, it can create a ball of plasma. Plasma is the fourth state of matter, after solid, liquid, and gas. And even though it makes up 99% of the visible universe, we didn't know plasma was a thing until the late 19th century. In 1879, Sir William Crookes, a British chemist, first discovered that he could make what he called radiant matter using a glass container with two electrodes in it, which he used to ionize the gas inside. This matter was later called plasma by American chemist Irving Langmuir in 1928 because he decided that it looked like blood plasma. Plasma is like a gas, but instead of containing neutral atoms or molecules, it's made of ions and electrons. So to create plasma, all you have to do is create conditions in which electrons get knocked off the particles in a gas. Sometimes this happens because the gas is hot. The extra energy knocks electrons out of their places, ionizing the gas. Other times, a powerful electric current can eject electrons from gas particles, turning that gas into plasma. But even though plasma essentially comes from gas, it acquires so many special properties that it's considered an entirely different state of matter. Normally, for example, gas isn't all that good at conducting electricity. Actually, it's often used as an insulator. But in plasma, there are so many detached electrons floating around, it becomes incredibly conductive. This conductivity shows up in lightning, for example. When a powerful electrical current forms between two highly charged areas in the atmosphere, it passes through a long, skinny column of air, heating it to 5 times the temperature of the surface of the sun. Lightning is actually a trail of plasma. And since electric fields and magnetic fields are both the result of the same force, electromagnetism, plasma also turns out to be very responsive to magnetic fields. Researchers often use this when they're trying to control the stuff, to study it. But we also use plasma all the time in our everyday lives, like in fluorescent lights. When you turn on a fluorescent light, an electric current ionizes the gas in the bulb, usually argon with a little mercury, and it becomes plasma and interacts with a compound called phosphor to create light. So sure, you'll find plasma in all kinds of places on Earth, but in space, the stuff is everywhere. Stars, for example, are just giant balls of plasma. The tremendous heat generated by their fusion reactions has the same effect on atoms of gas as found in a Crookes tube or a fluorescent bulb, only much, much, much more so. And there's plasma between stars too, even between galaxies. We normally think about the space between stars and galaxies as a vacuum, and a lot of it essentially is, but there are a lot of places that have quite a lot of matter. It's just spread out over light years of empty space. And that too is plasma, pockets of gas that have been superheated into clouds of ions and electrons. Cosmologists think that up to 50% of the normal matter in the universe is strewn around between galaxies in this form, known as the intergalactic medium. So you don't have to be an old-timey sailor to witness the fourth state of matter. It's right over your head in the fluorescent lights and outside your window the next time a thunderstorm comes, and, well, all over the universe. Thanks for watching this episode of SciShow, especially to our Subbable subscribers who keep us energized. See what I did there? To learn how you can support us, just go to Subbable.com to learn more, and don't forget to go to YouTube.com/SciShow and subscribe.
There are all kinds of things astronauts can do on board the International Space Station that we simply can't do here on Earth, like float, or simply gaze upon the Earth from a very rare vantage point, or create the fifth state of matter. There are 4 natural states of matter. Can you name them? They are solids, liquids, gases, and plasma. But in the extreme conditions of space, a strange and exotic 5th type of matter, known as Bose-Einstein condensates, can take shape. We'll refer to them as BECs. As you might have guessed from the name, Albert Einstein had a hand in predicting BECs, along with Indian mathematician Satyendra Nath Bose about 100 years ago. The substance forms when atoms of certain elements are trapped using lasers and cooled to near absolute zero. That's 0 degrees Kelvin or minus 273.15 degrees Celsius. Bitterly, bitterly cold. At that point, atoms stop behaving individually. Instead, they clump together and act like a single quantum object with both wave and particle properties. BECs are also very fragile, so studying them on Earth is almost impossible, and labs can only maintain them for milliseconds. Scientists have been experimenting with them on Earth since the 90s, but in microgravity, BECs can last more than a full second. Astronauts created them from atoms of a soft metal called rubidium using something called the Cold Atom Lab, which was sent to the ISS in 2018. So why go to all the work of creating BECs at all? Well, they can be used to study quantum mechanics on a macroscopic level, which opens up all kinds of doors. Everything from improving spacecraft navigation to simulating the possible conditions inside a black hole to unlocking the mysteries of dark energy. What they've achieved on board the ISS is more of a technological win for now, but it's a taste of what might be possible one day in the future. For Space TV News, I'm Cambry Caldwell.
Solid, liquid, gas.
Super solid, super fluid.
Or Bose-Einstein condensate.
That one is super cool.
It is plus plasma.
But we haven't even gotten started yet. We truly live in the future.
You ready, T?
Ready.
Scientists have created yet another state of matter.
Woo! Yay! It's called a super solid, and while it sounds like a solid, it's
not. A super solid is basically a super fluid that got its crap together.
And by crap, you mean molecules.
I do. The researchers who created the new state of matter took a Bose-Einstein condensate made of sodium gas and used lasers to cool it to near absolute zero.
The atoms are moving extremely slowly. A BEC is a special phase of matter created in 2001, winning researchers the Nobel Prize for Physics.
Once cooled to a BEC, the sodium flowed with zero friction. It's like a super fluid. a superfluid, which is awesome. The BEC was also superconductive, meaning its electrons move through it with zero resistance. There are numerous scientific benefits to these two conditions, but we're not here to talk about that.
In this case, the scientists kept cooling that sodium, and at some point it arranged into a non-crystalline solid.
The scientists called it a superfluid flow with long-range spatial periodicity of a solid.
Those are some fancy science words.
They sure are. Essentially, think of it like a coffee cup filled with a frictionless superconducting gel that if you could stir it, would never stop going around.
Delicious. The fluid didn't suddenly become hard. Instead, it's not exactly solid. Think of it like a gel. It's a fluid, but it behaves like a solid.
They've still got a lot to learn about these fluids/solids, but according to their paper, their supersolid, quote, establishes a system with continuous symmetry-breaking properties, associated collective excitations, and superfluid behavior.
Let's break that down.
That's a lot, yeah.
Superfluid behavior you get, we just explained it, frictionless superconductor.
Collective excitations is a fancy way to say quasi-particles. Quasi-particles are a group of particles that behave as if they're one because their parts are interacting somehow.
And then there's symmetry breaking.
That's also describing particle movement. Normally in quantum mechanics, symmetry is a big deal. Breaking it, a bigger deal.
At the moment, it continues that old saying, the closer you look, the stranger things get.
But come on, do we really have 6 states of matter now? No, we don't. We have way more. The states of matter, solid, liquid, and gas that you've been living with your whole life were never all there were.
It's kind of like when you're learning math. First, you're taught numbers. Then they tell you there are infinitely many numbers. Then, as if they're just messing with you, they tell you there are infinite negative numbers too.
And then you find out there are irrational numbers and imaginary numbers, and you can do calculations with infinities and embedded equations into each other, and yeah, matter's like that.
So yes, solid, liquid, gas, and plasma exist, but it's really about molecular arrangement. Solids are interacting heavily, liquids are more loosey-goosey, and gases are just barely interacting, while plasma is free. It can do anything. But on top of those 4, there are several more states of matter.
Cold ones like the Bose-Einstein condensate, and supersolid, and hot ones like electron-degenerate matter, free particles found in white dwarf stars, or the theorized stranger matter, possibly found in neutron stars.
Plus, of course, time crystals, which have low energy states and weird effects across time symmetry.
I mean, we should just do a whole video about states of matter, right?
Yeah, we probably should. Bottom line, we have a new state of matter, yay, but we don't have 6 or 7. We have at least a dozen. They're just more out there, experimental, laboratory only, or extreme kinds of matter.
Our universe? It's pretty awesome.
Boom diata.
Shakalaka. Look everyone, if you want to know more about states of matter, watch this video about time crystals. It'll give you a nice headache, or maybe it already has. Do you have an itch for science to answer? That's why we're here. Tell us in the comments, subscribe for more, and thanks for watching Seeker.
Bye.
Bye.
Look at this instrument. Do you know what it's called? Yes, it is a trumpet. Would you believe that it started out looking like this? A flat piece of metal? Metal is made of matter. So is everything around you. Matter is anything that takes up space and has mass. And matter can be changed or combined to make other things. Look at this piece of paper. You can fold it, cut it, tear it, stack it, or crumple it. Even though it is changing shape and size, it is still paper. Some scientists study what things are made of and how they can be changed. This is a civil engineer. She builds and designs bridges using a lot of different materials. If you change matter, does it stay that way forever? Changes to matter can be temporary or permanent. We call temporary changes reversible changes. A reversible change means that the matter can go back to the way it was before you changed it. When you mould, fold, or bend something, you can reverse it. It can be put back the way it was before. This sculptor pushes and smashes down a block of modelling clay, then smooths and pats it into shape. At the end, the sculptor can mush it back into a lump of clay and start all over again. We call permanent changes irreversible changes. Can you think of some examples of irreversible changes? An irreversible change means that the matter cannot be put back exactly the way it was before. If you cut, tear, or burn something, that change is irreversible. If you cut a loaf of bread into slices, or tear a piece of paper into parts, you cannot put it back together exactly the way it was. When you put a raw egg in a pan and cook it, is that an example of a reversible or irreversible change? That's right, it's an irreversible change. You can combine different pieces of matter to make something. For example, you can combine many small building blocks to build a larger structure.
They have to put monster spawners in here.
You can also combine and build things in a game. While the materials in a video game do not have real mass, they are treated like matter in the game. Civil engineers often use computers to test their designs before building them in real life.
This is how it will look when it's done, and it's almost there.
The same process of combining materials happens when building a trumpet. This machine cuts a sheet of metal into smaller pieces. Different pieces are bent and turned into new shapes. Next, the metal is heated so it can be smoothed into another shape. It is also combined with other pieces of metal that have different shapes. Step by step, the object goes through reversible and irreversible changes. Eventually it forms a trumpet. So when you are at school, home, or playing with your friends, take a look around and try to spot the matter around you. For example, think of a piece of wood. What are some of the ways you may be able to change it? Would these changes be reversible or irreversible?
How would you describe these objects? How about red? Or shiny? Maybe rough? Light? Or heavy? When you describe an object's color, texture, size, or shape, you're describing its properties. Over time, people have learned how to manipulate matter to make things that have properties with the characteristics they want. Soft, hard, smooth, bouncy, or heavy. Think about the way transportation has changed over time. The first steam locomotives in the 19th century were made mostly of iron, a material known for its high tensile strength. An object's tensile strength is how much it can be stretched without breaking. Iron is also malleable, which means its shape can be changed easily. Iron is easy to hammer into thin sheets. Tensile strength and malleability are also properties of matter. Iron is even stronger when it's combined with carbon. When you heat up iron and carbon to very high temperatures, you can make steel. Steel is both strong and durable, which means it won't wear out quickly. These properties make steel more useful than iron for building almost anything that needs these properties. Strength and durability are also properties of matter. But you wouldn't want to build an airplane out of steel. For that, you need aluminum, a material that's light but still strong. The Wright brothers' first airplane engine had an aluminum crankcase, and lightweight aluminum is still used in all types of aircraft to this day. It's also used in high-speed trains and some cars too. The properties of matter help us make decisions about the things we buy. For example, today, color is one of the key factors we consider when choosing a new car. But it wasn't always even an option. When Henry Ford started selling Model T cars more than 100 years ago, he told his customers, "You can have any color as long as it's black." But as the technology of paints improved, cars were painted in all different colors. Bike manufacturers are always finding new ways to manipulate matter to make bikes lighter, yet still durable. Bike chains are another thing that bike manufacturers are in a quest to improve. Traditional chains get grimy and dirty because their metal links need to be greased, and that attracts dirt. But now bike companies are using new materials to replace these chains with grease-free alternatives, such as plastic cables. One company in Hungary makes cables using a plastic called polyethylene. It's the most common plastic in the world.
Polyethylene can be made into soft plastic water bottles. It can be made much more rigid. It's one of the most remarkably versatile plastics out there.
Polyethylene gives bike cables the strength of metal, but the cables don't need to be greased, so they stay cleaner, longer, and never rust. Some scientists work in a field called materials science, understanding how matter is put together and trying to design improved materials. Materials scientists experiment with materials that can make bikes lighter, cars tougher, boats more scratch-resistant, and train brakes more shock-resistant. All characteristics that help make travel safer and more efficient. So take a look around, pick an object, and describe 5 of its physical properties. Then ask yourself, what materials are giving them those characteristics?
To those of you worried about the hysteria being promoted by our idiotic hive mind and media that our science is dying, I say take heart. That couldn't be further from the truth. This story is proof. Okay, there are 4 states of matter that we encounter in our everyday lives here on Earth, right? Gas, liquid, solid, and plasma. We've known this for centuries. But about 100 years ago in the early 1920s, scientists including Albert Einstein theorized a 5th state of matter, which has become known as the Bose-Einstein condensate, or BEC. Basically, a BEC is a gas that is cooled to a temperature of nearly absolute zero at negative 273 degrees Celsius, at which point it stops behaving as a gas of individual atoms and particles, but rather acts as an entity in a single quantum state. As such, BECs can offer scientists a way to study the workings of quantum mechanics, which could explain a hell of a lot about the mysteries of our universe and the way everything works. Which is why it was so exciting for scientists to be able to produce this 5th state of matter in a lab back in 1995 for the first time. And since then, labs across the planet have been able to do so by supercooling gases. However, the only problem has been that scientists have only been able to keep BECs stable for a split second before they collapse under the Earth's gravity. So they've been able to make them for 25 years, but they haven't been able to study them too much. Until now. Because just now, scientists have been able to generate BECs outside of the Earth's gravity on an experiment aboard the International Space Station. They used something called the Cold Atom Laboratory, which was launched up there a couple of years ago. It's a suitcase-sized device that chills atoms in a vacuum chamber. And now scientists have been able to use it to create BECs that remain stable for many seconds, allowing them much more time to study them before they collapse. Researchers hope to use the experiment to watch atoms collide on a quantum level, and also probe the ripples in space-time gravitational waves, which would produce a level of scientific knowledge that is absolutely mind-blowing. I mean, we are getting closer and closer each and every day to unlocking the secrets of the universe. To me, that's as big as seeing the face of God. Some might say it's one and the same. But no matter what you want to call it, it's an undeniable, massive scientific achievement. So yeah, if the idiotic hive mind and our media have you worried that our science is dying, take heart. The only thing dying off is them, perhaps thanks to their idiocy. But our science, it is very much alive and well.
Hello mortals. Have you ever wondered what you would look like on an atomic level? Or how much space in a container you would take if you accidentally liquefied yourself? Maybe you've wondered about the possibility of changing the atoms of an entire planet to form one giant pizza in the shape of an L on your forehead. Well, if you didn't wonder about any of it, this video will grant you the knowledge about the wonders of matter, a lot of which you've most likely never heard of. We'll start with the first 4 most common states of matter. These are the ones that allow you to do everything: eat, sleep, watch this video, complain about your life and do nothing to change it. And the list goes on. Aside from depression, your current state at the moment is the solid state. In a solid, constituent particles are closely packed together. The forces between these particles are so strong that they cannot move freely, but only vibrate. Something else that's long and vibrates is an electric toothbrush. And as a result of that, a solid has a stable, definite shape, and a definite volume. Solids can only change their shape by an outside force, as when broken, cut or smashed by something heavy like the debt of the United States. Now on to the liquid state. A liquid is a nearly incompressible fluid that conforms to the shape of its container but retains a nearly constant volume independent of pressure. These liquids can be as colorless as the void from which I edit videos in. The volume of a liquid is definite if the temperature and pressure is constant. When a solid is heated above its melting point, say iron, it becomes a liquid at 1538 degrees Celsius, and for the Americans, 2800 degrees Fahrenheit. Intermolecular forces are still important, but the molecules have enough energy to move relative to each other and the structure is thus mobile. This means that the shape of a liquid is not definite but is determined by its container. The volume is usually greater than that of the corresponding solid. The best known exception being water. The gaseous state. The state that most kids like to make jokes about. A gas is a compressible fluid. Not only will the gas conform to the shape of its container but it will also expand to fill the container. In a gas, the molecules have enough kinetic energy so that the effect of intermolecular forces is small or zero for an ideal gas. And the typical distance between neighboring molecules is much greater than the molecular size. A gas has no definite shape or volume just like a liquid, but occupies the entire container in which it is confined. Just like your mom. Now before we talk about the next one, we forgot the one that every nerdy kid likes to remind the teachers about. Can you guess it? What are we going to talk about next? A. Gamer girl bath water. B. A superfluid. C. Plasma. Or D. Liquid debt. Despite all odds, the correct answer is C. Plasma. Now like a gas, plasma does not have definite shape or volume. But unlike gases, plasmas are electrically conductive, produce magnetic fields and electric currents, and respond strongly to electromagnetic forces. Positively charged nuclei swim in a sea of freely moving dissociated electrons. Similar to the way such charges exist in conductive metals. A gas is usually converted to a plasma in one of three ways. Either from a huge voltage difference between 2 points, by exposing it to extremely high temperatures, or by taking the gas and putting it in a bottle and then let it get struck by lightning in Minecraft. Heating matter to high temperatures causes electrons to leave the atoms, resulting in a lot of free-moving electrons. This creates a so-called partially ionized plasma. At very high temperatures, such as those present in stars, it is assumed that essentially all electrons are as free as the Karens making a ruckus in America. This forms the so-called fully ionized plasma. Now before we continue, we partnered up with PureVPN to bring you an awesome deal. Now more than ever, a VPN can be a lifesaver, and this one is the highest rated provider on Trustpilot. PureVPN has an almost flawless rating, based on more than 10,000 reviews. It is a reliable service with over 2,000 servers in more than 140 countries. It secures your connection on all of your devices with easy-to-use apps across all major platforms. PureVPN also gets you all kinds of online deals at a cheaper price by connecting you to different regions. As an example, it can save you money on Steam games and flight tickets. Some of their new cool features include the fact that they help you stream all you want, including the newly added Disney+, and 7 Netflix regions and many others. Try Pure VPN for 1 week for just 99 cents with full access and no restrictions. The link is in the description below. Moving on. Phase transitions. That's how we describe going from one state to another. Not by car, but by sublimation, from solid to gas. Deposition. Going from a gas to a solid. Ionization, in which atoms, well, get ionized. Deionization. Freezing. Melting. Vaporization and condensation. There are a lot of other states of matter as well. For example, low-temperature states. These include superfluids, a liquid close to absolute zero. Because it has no viscosity, it can climb the walls of the container like here. The Bose-Einstein condensates. Discovered by, you won't believe it, Satyendranath Bose. A Bose-Einstein condensate is colder than a solid. It may occur when atoms have very similar or the same quantum levels, at temperatures very close to absolute zero. It also results in some nice phenomena. Fermionic condensates. Pretty similar to the Bose-Einstein condensate but composed of fermions, particles that generally have half-odd integer spins. Rydberg molecules. One of the metastable states of strongly non-ideal plasma is Rydberg matter, which forms upon condensation of excited atoms. These atoms can also turn into ions and electrons if they reach a certain temperature. The quantum Hall state. A quantum Hall state gives rise to quantized Hall voltage measured in the direction perpendicular to the current flow. Photonic matter. Photonic matter is a phenomenon where photons interacting with a gas develop apparent mass and can interact with each other, even forming photonic molecules. Dropleton. A quantum fog of electrons and holes that flow around each other and even ripple like a liquid, rather than existing as discrete pairs. We also have high-energy states and very high-energy states. In these we have degenerate matter, quark matter and color glass condensates. All of the previous are high-energy states, but we also have very high-energy states. An unknown state has created the baryon asymmetry in the universe, but little is known about it. In string theory, a Hagedorn temperature is predicted for superstrings at about 1030 Kelvin, where superstrings are copiously produced. At the Planck temperature of 1032 Kelvin, gravity becomes a significant force between individual particles. No current theory can describe these states and they cannot be produced through any foreseeable experiment. However, these states are important in cosmology because the universe may have passed through these states in the Big Bang.
This is a liquid. This is a gas. And this? Well, this is a solid. Now, the amazing thing is that they're all made of the same stuff. Now, what is this stuff? Well, stick around.
Built by the science guy. Built by the science guy.
Science rules.
Built by the science guy.
Inertia is a property of matter. T minus 7 seconds.
Bill Nye the Science Guy.
Bill Nye the Science Guy is brought to you by Matter. Matter is everything and all stuff. Stand by for Matter.
Ever wonder what the universe is made of? Well, the universe is made of matter. And matter is stuff. Everything that you can touch is matter. And matter comes three ways, what we call phases. Matter is either a solid, a liquid,
it's liquid,
or a gas. That's what those bubbles are. Matter can be very refreshing.
That is molten steel. Now, the only difference between molten steel, melted steel, liquid steel, and solid steel is energy. That's right. The atoms in solid steel are moving a little more slowly than the atoms in liquid steel. Kind of wild.
The gas in our cars changes from a liquid we call gasoline to a gas, to a vapor. Our cars run on a gas.
A gas. The balloons are filled with a gas. Solid, liquid, gas. They're all phases of matter. It's chemistry. You just mix in a little energy and, you know, we should be in the lab.
The what?
The lab. No, where's the lab? Anybody seen the lab?
Where's the lab?
We need to go to the lab.
The lab.
Oh, here it is. Getting things to change phase takes energy. So take a look at this. It's liquid water, and we're heating it with energy from this burner. Above the liquid is water vapor. It's invisible. The molecules get more energy and they change phase to a gas. See, the liquid is becoming water vapor. It's changing phase into a gas. Now, what if we wanted to change phase again? Like, let's say we wanted to turn this liquid into something else. Like, maybe we want to turn this liquid into a solid. Now, how would we do that? We'd have to take energy away, right? What do you think we'd need? Well, maybe a freezer. Maybe a great big stainless steel freezer of science, like this one. Take a look inside. It's cold. It's real cold. Oh, it's like -4 degrees Celsius. Now, where does the energy go? Where does the heat go that was in this freezer? You can't just throw it away. That would be a violation of the first law of thermodynamics.
What?
Now, the heat has to go someplace. Well, take a look up here. See that thermometer? It says like 28 degrees Celsius. That's warm. That'd be like a very warm summer day. So what the freezer does is pump the energy, pump the heat from out of the freezer into the room. Now, if you can do that enough, you can make things change phase. Take a look at this. It's a great big popsicle of science. Solid ice. We changed the liquid from that mold into a solid. Made it into this popsicle. Oh, that's a good one. That's a real good one. Phase change. It's great fun at parties.
Changing a solid to a liquid to a gas always requires the same thing.
Pure energy.
And you can change a solid to a liquid to a gas just by taking some ice cubes out of the freezer and frying them up.
Here's some fried ice that we prepared earlier. Not bad, eh?
There's nothing there, Martin.
Well, of course not, Michaela. You can't see water vapor.
Then why don't we show them something they can see?
Good idea. Hit it.
Careful. Ooh, ooh, watch it. Ooh, ah, ooh, 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 ah, ooh, ah. Ooh, ah. Ooh. Watch it.
Those are some pretty excited molecules, huh, Martin?
I'll say it. They were so excited, they vaporized.
Steam you can see is made of droplets, liquid water. When it disappears, it's an invisible gas, water vapor.
And you can make fried ice at home, too. Just make sure you have adult supervision so nothing gets overcooked.
See ya.
Energy can make things change phase. Like, this burner is providing energy that makes this liquid water change to water vapor. It's changing phase from a liquid to a gas. Now watch this. This is liquid nitrogen, and it's going to change phase too. I'm going to pour it into this flask, and it's changing from a liquid to a gas without the help of a burner. It doesn't need it. That's because it's so cold, minus 196 degrees Celsius, that the energy in the room is able to make it boil. This stuff looks kind of dangerous, doesn't it? But it's nitrogen. It's the same gas that's between you and the television. 78% of our air is nitrogen. So,
The heat from the room makes the molecules move faster and faster, and they get farther and farther apart. And they change from a liquid to a gas. Now, what happens when molecules slow down? Well, they get closer and closer together, and some unusual things can happen. Here, let's try something. We'll take this, it's a rubber ball, this, ordinary onion, and a few of these, marshmallows. And we'll put them in liquid nitrogen and let them cook for a while. Come back in a couple minutes and we'll see what we get. If you just joined us, we've been cooking with liquid nitrogen. Liquid nitrogen is minus 196 degrees Celsius. It makes molecules slow down and get closer together. Here, watch. It's an ordinary rubber ball. Here's an onion. Oops. Liquid nitrogen gives you an unusual way to slice it. And these are marshmallows. They've been cooking for a while. You don't need a campfire.
Careful. Oh, watch it. Oh,
So now you know the three phases of matter. Solid, like this ice. And liquid, like this water. And gas, like this water vapor.
Here's the story of Johnny Atom, who is everywhere and everything we know. He is solid, liquid, gas, every matter. That's how the phases go.
Here's the story of the same guy, Johnny. He makes chemistry and science really fun. He is all things, he's all around us. He's the atomic one.
Energy and Johnny Atom work together, making all the matter change from state to state. Molecules, compounds, and even plasma. It goes to show you chemistry is really great. He's Johnny Atom. He's Johnny Atom. He's solid, liquid, gas. He's everything.
Welcome to the absolute zero hour. Now, we're not going to reach absolute zero, and it's not going to take an hour, but it's kind of a cool name, isn't it?
Okay.
Now, cool is just what I want to talk about today. See, this is a box of ice water. It's as cold as when you put ice in a soda. And here is a ball filled with air, and it's connected to a pressure gauge, an absolute pressure gauge. So the higher the pressure in the ball, the higher the gauge will read. You know, what's pressure? Well, it's like moving molecules. The faster the molecules are going, the higher the gauge will read. And the slower the molecules are going, the lower the gauge will read. Okay, I'm going to move the ball from here to here. Now in here we have dry ice. That's solid carbon dioxide mixed with a little alcohol, so it's still a liquid. Now this is colder than it is anywhere on Earth. This is colder than it is in Antarctica. It's colder than the South Pole. You see the molecules slow down and the gauge reads a lower number. Think of it this way. Here's the old molecule machine. Think of these plastic balls as molecules. And when the machine is going this fast, that's like the ice water. So this is like a pressure gauge. And it reads this high when it's in the ice water. Then, when I lower it here, that's the pressure of the dry ice bath. So you see, the slower the molecules are going, the lower the pressure reading. Well, let me ask you this. Suppose there was no motion at all. Molecules completely stopped. Absolutely stopped. Well, that would be what scientists call absolute zero. It would be colder than almost anything you can imagine. And the reason is there'd be no molecular motion whatsoever. So try this. We're going to put the ball of air of science into this special freezer. We're going to imagine that it's going to get very, very cold. Now, could we get to absolute zero? Actually, no.
Absolutely no.
What?
If you called a travel agency and said, hey, take me to absolute zero, they'd have to go, we can't. You can't get there. Absolutely not. Isn't that weird? Now, why is that? Think of it this way. Here's the ball of air, right? It's pretty cold. It's connected by this tube to this clamp. And this clamp is connected to the base of this refrigerator. And the refrigerator's on the table, and the table's on the floor, and the floor's in the building, and the building is on the earth. So there's always a path for heat to get from the earth into the building, up onto the floor, up to the table, into the freezer, down this rod, into the ball of air. There's no way for the ball of air to be completely separated from some source of heat. There's always a way for heat to get to the air. You can never quite get to absolute zero. So you can't ever get to absolute zero. Zero! The scientists have gotten within 1,000th of a degree Celsius, but they've never gotten there, and they never will. Absolute zero. Zero is more of an idea than a real thing you can get. We can get within 1,000th of a degree, but we can't quite get there. There's no way. Absolutely no way. But the idea is kind of cool, isn't it? In fact, very cool. Thank you for watching the Absolute Zero Hour. That's a solid.
Solid.
Here's a really neat experiment. You'll need a jar that can take boiling water to do this phase change, like maybe an old jelly jar. In here I have a cup of boiling water and 2 cups of sugar. Now I'm going to pour the sugar water into this jar.
Whenever you're using a stove, be sure to have an adult around.
Careful. Watch it. Watch it.
Now I've tied a piece of string to a pencil, and I'm going to set the pencil in the jar like this. And that's it. I leave everything sitting here until it cools down. Then later I cover the top with plastic wrap and put it where it won't be disturbed. Rock candy. It used to be a liquid, and now it's a solid. You can even add food coloring to make them any color you like. Sometimes science is very sweet.
This is solid carbon dioxide. We can change it into a gas immediately by putting it in warm water. Watch. Solid. Changing phase from a solid to a gas, which is pouring out of the spout of the pop bottle of science. And we apply the balloon, and it inflates rapidly. That's carbon dioxide gas. Not bad, huh?
It's a gas!
I'm Maggie Steen, and I'm a quality control scientist for Coca-Cola. And it's my job to make sure there's just the right amount of fizz in this can. We make 1,450 cans a minute on this line. This is where we keep the CO2 in the silos. It's a liquid form here. It's kept under high pressure so it stays a liquid. It goes through the heaters. It becomes a gas where then it goes into the filling system and it gets in our cans of pop. We shake the bottles and we test the pressure and the temperature, and with the temperature and pressure we can look on a CO2 little computer that we have and tells you the actual volumes of CO2 in there. If there's no carbonation in there, it's really flat. It's lost all its pizzazz. There's no point in drinking it, really. I mean, I think people drink it because it's carbonated. So I've been here 16 years and it's still fascinating.
Solid, liquid, gas. 3 phases of matter. Solid, molecules are moving slowly, packed close together.
Solid.
Liquid, molecules are moving a little faster. They're able to flow a little bit.
It's liquid.
Gas, molecules are moving very fast. They're just wild.
It's a gas!
3 phases of matter.
When When matter is a gas, a lot of the time you can't see it. It's invisible. But here's a way to prove to yourself and any of our fellow scientists that invisible gas is matter. We'll weigh it. First, take a look at this broomstick balance of science. It's a broomstick with a hole in it. There's a lunch bag tacked to each end. Now we need to make some invisible gas. This is an old trick, but it's a good one. Pour some vinegar into a pitcher. Then add a little bit of baking soda. That fizzing is carbon dioxide gas coming off. It's the same gas that bubbles out of our soft drinks. Even though it's invisible, you can still pour it just like you pour water or milk. Pour the invisible gas into one of the bags. It pours even though you can't see it. The gas is heavier than the air and the bag on this end goes down. It's invisible, but it's matter. It's in the phase of matter that we scientists call gas. It's a gas! And it's total science.
Okay, today we're going to be working with some molten wax.
Looks just like chocolate.
And I'll have one of you pour that in for us. Aha!
Phase 1. The wax goes into the mold.
Okay, now we're going to let that cool. Okay, now that the wax has gone to a solid, we can lift it out of the pattern. Pop it. And there we are.
Whoa,
We've got our pattern.
That's neat. What do you need the water for?
We're going to mix that with the plaster and sand.
Oh.
This is going to get rock hard in about 15 to 20
Is this
minutes.
like cement?
Like cement, yes. It'll be all right.
Oh yeah, so that's
Okay, stick it down in there.
Phase 2. The mold goes into the plaster.
I think there's going to be like fire or flames or something that he's burning this stuff from, and we don't want to get burned from it, so we're wearing this stuff.
What we're doing is we're taking some silicon bronze and we're melting it down at about 2100 degrees Fahrenheit. And the first pour.
Phase 3. The molten metal goes into the mold. Solid, liquid, solid. Break.
Okay.
Solid, 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 liquid, liquid, solid. You go, Doc.
Look what we've got.
What's
Oh,
this
yeah.
one say? That's all there is. Let's get some hot dogs.
A solid sits on its stand. A liquid flows and runs out of my hand. There's a gas in this balloon. Now it's in the room. Science. When matter's in the gas phase, it takes the shape of its container. When matter's in the liquid phase, it takes the shape of its container. When matter's in the solid phase, it holds its shape. Many solids hold their shape even when you hit them with a water balloon. Well, you know what I mean. Gases, liquids, solids, science.
All matter forms, gas, liquid, and solid. We got a clue from some famous scientists. They took a look when the water turned to gases. Then they conclude everything is made of matter. Small particles, just take a look around. Change temperature, then the elements transform. It warms my brain to think of all of that change. Just take a look, form a shape or rearrange. This was so cool that they finally formed a theory. The elements formed on solids, liquids, and gases. Some elements, when combined with other matter, make such a change that they stay that way forever. Some other things change from one form to another when temperature is made hotter or cooler. All molecules moving slower or faster cause elements to change their form of matter. The ocean and the air are made of molecules together all the time, often changing rules from solids, liquids, gases. scientists, we have learned all that matter is to life, what beat is to rap. Cause it's cool right now, it's hot right now, it's gas right now, it's liquid right now, it's solid right now, changing phases right now, and I'll tell you now, science is cool right now, it's cool.
Oh, excuse me. Just doing some cooking, you know, changing some phases of matter. Right here I've got a solid boiling in a liquid, and I'm getting a gas. Well, thanks for hanging out with me today, but right now I got some serious phases of matter to change. See you around the universe.
Produced in association with the National Science Foundation.
Well, got some phases of matter to change. See you around the universe. Pretty cool. Well, got some phases of matter to change. See you around the universe. This is a liquid. This is a gas. And this, well, this is a solid. Now, the amazing thing is that they're all made of the same stuff. Now, what is this stuff? Well, stick around.
Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Bill Nye the Science Guy is brought to you by Matter. Matter is everything and all stuff. Stand by for Matter.
Ever wonder what the universe is made of? Well, the universe is made of matter. And matter is stuff. Everything that you can touch is matter. And matter comes three ways, what we call phases. Matter is either a solid, a liquid,
It's liquid.
or a gas. That's what those bubbles are. Matter can be very refreshing.
That is molten steel. Now, the only difference between molten steel
Those are some pretty excited molecules, huh, Martin?
I'll say. They were so excited, they vaporized.
Steam you can see is made of droplets, liquid water. When it disappears, it's an invisible gas, water vapor.
And you can make fried ice at home, too. Just make sure you have adult supervision so nothing gets overcooked.
See ya.
Energy can make things change phase. Like, this burner is providing energy that makes this liquid water change to water vapor. It's changing phase from a liquid to a gas. Now watch this. This is liquid nitrogen, and it's going to change phase too. I'm going to pour it into this flask, and it's changing from a liquid to a gas without the help of a burner. Doesn't need it. That's because it's so cold, minus 196 degrees Celsius, that the energy in the room is able to make it boil. This stuff looks kind of dangerous, doesn't it? But it's nitrogen. It's the same gas that's between you and the television. 78% of our air is nitrogen. So, the heat from the room makes the molecules move faster and faster, and they get farther and farther apart. And they change from a liquid to a gas. Now, what happens when molecules slow down? Well, they get closer and closer together, and some unusual things can happen. Here, let's try something. We'll take this, it's a rubber ball, this, ordinary onion, and a few of these. marshmallows. And we'll put them in liquid nitrogen and let them cook for a while. Come back in a couple minutes and we'll see what we get. If you just joined us, we've been cooking with liquid nitrogen. Liquid nitrogen is minus 196 degrees Celsius. It makes molecules slow down and get closer together. Here, watch. It's an ordinary rubber ball. Here's an onion. Oops. Liquid nitrogen gives you an unusual way to slice it. And these are marshmallows. They've been cooking for a while. You don't need a campfire.
Careful. Oh, watch it. Oh,
So now you know the three phases of matter. Solid, like this ice. And liquid, like this water. And gas, like this water vapor.
Here's the story of Johnny Atom, who is everywhere and everything we know.
Melted steel, liquid steel, and solid steel is energy. That's right. The atoms in solid steel are moving a little more slowly than the atoms in liquid steel. Kind of wild. The gas in our cars changes from a liquid we call gasoline to a gas, to a vapor. Our cars run on a gas. A gas. The balloons are filled with a gas. Solid, liquid, gas. They're all phases of matter. It's chemistry. You just mix in a little energy and, you know, we should be in the lab.
The what?
The lab. No, where's the lab? Anybody seen the lab?
Where's the lab?
We need to go to the lab.
Oh, here it is.
Getting things to change phase takes energy. So take a look at this. It's liquid water, and we're heating it with energy from this burner. Above the liquid is water vapor. It's invisible. The molecules get more energy, and they change phase to a gas. See, the liquid is becoming water vapor. It's changing phase into a gas. Now, what if we wanted to change phase again? Like, let's say we wanted to turn this liquid into something else. Like, maybe we want to turn this liquid into a solid. Now, how would we do that? We'd have to take energy away, right? What do you think we'd need? Well, maybe a freezer. Maybe a great big stainless steel freezer of science, like this one. Take a look inside. It's cold. It's real cold. Oh, it's like minus 4 degrees Celsius. Now, where does the energy go? Where does the heat go that was in this freezer? You can't just throw it away. That would be a violation of the first law of thermodynamics.
What?
Now, the heat has to go someplace. Well, take a look up here. See that thermometer? It says like 28 degrees Celsius. That's warm. That'd be like a very warm summer day. So what the freezer does is pump the energy, pump the heat from out of the freezer into the room. Now, if you can do that enough, you can make things change phase. Take a look at this. It's a great big popsicle of science. Solid ice. We changed the liquid from that mold into a solid. Made it into this popsicle. Oh, that's a good one. That's a real good one. Phase change. It's great fun at parties.
Changing a solid to a liquid to a gas always requires the same thing.
Pure energy.
And you can change a solid to a liquid to a gas just by taking some ice cubes out of the freezer and frying them up.
Here's some fried ice that we prepared earlier. Not bad, eh?
There's nothing there, Martin.
Well, of course not, Michaela. You can't see water vapor.
Then why don't we show them something they can see?
Good idea. Hit it.
Careful. Oh, watch it. Oh,